Hi folks, it's Mr. Wilshaw again here with another explainer. This time we're looking at 0654, Winter 21, question paper 4.1, and we're looking at question 3, which is all about light. Okay, we're going to talk through the answers. Ideally you should have done this question before you watch the video. However, you may be sitting there stuck and not really knowing what to do, and that's exactly the aim of my video, is to help you with any questions like that. Let's go for it. First question, 1 mark, state the speed of electromagnetic waves in a vacuum. Now, you may be surprised by this. This is a question that a lot of students get wrong. Maybe because they misread it, or maybe they forget what an electromagnetic wave is. Well, when we're talking about the speed of electromagnetic waves, we're simply talking about the speed of light, okay? Because light is an electromagnetic wave. And that value is 3 times 10 to the 8 meters per second, or 300 million meters per second, or even 300,000 kilometers per second. I've not put that on there. I would go with the left-hand answer there, the scientific notation, 3 times 10 to the 8 meters per second, purely because it's easy to write, okay, easy to remember, and very concise. Okay, and that number never changes in this kind of question because we're looking at the speed in a vacuum. The speed of light in a vacuum is always 3 times 10 to the 8 meters per second. We're then introduced to the electromagnetic spectrum, and it's worth reminding ourselves what the spectrum is. It's simply a family of waves which all travel at the same speed and have similar properties. Okay, and they differ in terms of their applications and also their wavelengths and frequencies. So we've got a common question here, which is to place a or maybe 2 features of the electromagnetic spectrum into the correct position. In this case, we're looking for visible light. Well, if you remember, violet is a color, red is also a color. Okay, and that they're going to belong to my visible light spectrum, and so therefore visible light neatly fits in between infrared and ultraviolet. Okay, now I put in the other guys, the gamma, the X-rays, the radio waves. You're not required to do this in the exam. However, every time I see these, I think you might I like to fill them in just to remind myself. Okay, the one that you need to do is visible light, and that goes in that middle position there. We're then asked to state the form of electromagnetic radiation that has the highest frequency. Now, again, this is one of these things that you can either remember, simply remember purely from fact, or you can kind of try and have a bit more system to it. I think remembering these things is quite easy at GCSE, is that gamma ray is the highest energy and therefore the highest frequency in terms of the rays that we use. And you know this because if you have exposure to gamma rays, and this can be quite dangerous to our bodies, and that's due to the high frequency, due to that high energy. Notice on our spectrum, in this case, it's on the furthest left. Okay, that's why I've drawn it in on the left-hand side. The left-hand side in this case represents the part of the spectrum with the highest frequency. Okay, let's move on. We're going to go and have a little look here at the transverse wave. Now, you remember what a transverse wave is a wave whose disturbance is perpendicular to its velocity. In other words, if we're moving from left to right, the disturbance might be up and down. Okay, so we use the word perpendicular when we're trying to define a transverse wave. In this one, all we have to do is use a double-headed arrow to label the wavelength, and I've done that on the screen now. There's a little cheeky bit by the question here. They offer you the chance to do it vertical or horizontal. This is a horizontal measure here, okay, because the wavelength is, for example, the distance between 2 neighboring troughs or 2 neighboring peaks, as I've shown on the screen. And there are various arrows you could draw here. Okay, but these are the easiest ones for us to visualize, which would be simply the distance between those 2 peaks. Okay, now if you were going for a vertical line, you're probably measuring the amplitude, and that is not quite the same. All right, let's carry on. A lot of little 1-mark questions in this one, which is quite a nice start to the paper. Last one here, as this part here, state the equation that links the frequency, speed, and wavelength of a wave. Okay. I've written this in words, you could write it in symbols. Speed is equal to the frequency times the wavelength. Okay, as some of you know, I do like to try and think of easy ways of remembering this, and I think one way you could remember it is using the mnemonic very fast waves, okay? V for the velocity or speed, fast, F for the frequency, waves, W for the wavelength, very fast waves. And so that way, if you are trying to remember your equations, this could be one way in. It's not foolproof, but it's a way I like to use when I'm trying to remember my equations. Okay, again, we'll come through. We're going to get into slightly harder bits. Okay, things first, we have got a thin converging lens. Okay, and you're asked to complete the figure 3.3 to show how the rays of light from the object form an image. Now, I've done this for you. Okay, we do this all the time. We need at least 2 lines. That's why 2 of the lines here are purple. One line goes horizontal through the top of through to the top side of the lens, and then through the focal point on the right hand side. Second line will go straight through the center without refracting, without bending, and we'll cross with that first line. Now I like to do a third line, which would be going through the focal point on the left hand side, through the lens, and then becoming horizontal to check that my lines all cross at the same point, and that crossing point is going to be where your image forms. Notice, in this case, the image is inverted. Okay, it is, and it is magnified. If you were to compare the size of the object to the image, then you would have a bigger image than the object, and we'll talk about that in a second. Another feature here is that the image is real, and you're often asked to discuss why that we know that this is real. Okay, we know that this is a real image is because the light rays actually cross each other. Okay, in a virtual image, we require a bit of processing, a bit of extra work in order to make our image, whereas in this case, those light rays are crossing each other, and therefore a real image would show on a screen, i.e. the light rays actually meet one another. And you can see that very, very clearly. Okay, in this case, we've got our light rays bending to form an image at the same point. Okay, last but not least, we're back onto a final 1 mark question. You can see I had a little trouble with this one actually. I wrote an answer and then I thought about it again. Okay, in this case we would use this as a magnifying glass. Let's talk about why. Well, if you notice here, as I said before, my image is enlarged. Okay, we've got a bigger image than the object, and therefore we would use this to produce a bigger image. Okay, and the case that you might use this is in a magnifying glass. Now you will. The reason that didn't come to mind straight away is because often we use magnifying glass in a slightly different way, is when the object is actually inside the focal length, and that's where we form a virtual enlarged image. In this case, we're forming a real enlarged image, but what Cambridge was looking for here was actually the magnifying glass. So make sure that you're thinking about the size of those images relative to the object when you're thinking about the use of a lens like this. Okay, I think that's all for question 3. As ever, if you've got questions, ask them. Okay, I'm more than willing to help you. If not, let's get on to question 6.